Atoms!
Hey, this is Matt and Max here.
And Max!
And we're here to talk about atoms.
Atoms!
Now, atoms are everywhere.
Everywhere!
They're in you.
In you and me!
Now, first, to learn about atoms, you need to learn
The history!
Good one, Max. So first, we're going to talk about Antoine Lavoisier and the law of conservation of mass. Now, Antoine Lavoisier stated that mass is neither created nor destroyed. For example, if we take a piece of paper
Take it.
and we rip it,
Rip it.
now mass has not been created or destroyed in this
It ain't
process.
destroyed.
All the mass that was originally here is still here.
It's there.
And this is what Antoine Lavoisier was trying to get across with his point. Thank you. Next, we will talk about the law of definite composition by Joseph Proust. And this states that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So let's say this glue stick and this hockey puck were combined. They will have the same exact mass as they did before they were combined. The law of multiple proportions was derived by John Dalton, and it stated that the mass of one element which combines with a fixed mass of a second element are in a ratio of whole numbers. So pretty much carbon monoxide, CO, will be in a ratio of 1 to 1, 1 carbon to 1 oxygen. And carbon dioxide, CO2, will be in a ratio of 1 to 2. Okay? Yes. From this, Dalton derived his own atomic theory. Dalton's atomic theory stated that elements are composed of extremely small particles called atoms. Now this is where atoms finally come into view in history. Now atoms, all atoms of an element are pretty much identical, as he said, having the same size, mass, and chemical properties. And he also said atoms of one element are different than all other elements. So every single element is unique in its own way. So atoms are made from 3 different subatomic particles: the proton, the neutron, and the electron. All 3 of these were derived from different scientists in different experiments. The first one was found, electrons is the first one we'll talk about here. And this was found by J.J. Thomson. He found that there was a negatively charged electron in the atom. And he found this by using the cathode ray tube. Now this is a picture of the cathode ray tube. So as you can see, there is a cathode here, which is a negative charged in the cathode ray tube, and there is an anode here, which is the positive charge in a cathode ray tube. A beam of electrons is shot through the cathode ray tube and then hits the fluorescent screen to stop it. Now, J.J. Thomson found out that there was a negative charged particle in an atom by placing a positive magnet right down here, and the beam of electrons bended towards the positively charged magnet. And that is how J.J. Thomson discovered that there was a negative particle called the electron in the atom. Now from this information, he derived his first model of an atom. This is called the plum pudding model of an atom, and this has electrons scattered out.
Negatively charged
Electrons, thank you, Max. Scattered out throughout the plum pudding, or the atom.
Or the chocolate chip cookie.
Yes, and it looks like a chocolate chip cookie or a plum pudding.
Not that I've ever seen a plum pudding.
Yeah, me neither.
I don't think anyone has.
So J.J. Thomson, he found out that there was a negatively charged particle in an atom called an electron, but he did not find the exact charge of an electron. So now, Robert Millikan and the oil drop experiment, he used the oil drop experiment to find the exact charge of an electron. Now this is a picture of the oil drop experiment. Now, as you can see, these are a bunch of oil droplets going into two positively and negatively charged plates. This is the positive charge plate up here. This is the negative charge plate. Now, there was a charged oil drop in the middle, and now Robert Millikan, he found out how to use these two just to make it centered, this charged oil drop. And he knew the mass of the oil drop, so he could find out that the oil drop in the center and the exact charge of an electron. So next we're going to talk about radioactivity. Now, radioactivity was discovered by Barkell. Now, he found out that atoms give off radiation, and that will change their properties. Now, there is an alpha, gamma, and a beta ray. Alpha is positively charged, gamma is neutrally charged, and beta is negatively charged. And they can all go through different things and not go through get stopped by different things. Alpha particles will be stopped by paper. Gamma particles will be stopped by lead and concrete, and beta particles are stopped by aluminum. Yes. Sure. Okay, so now we're going to be talking about Ernest Rutherford and the gold foil experiment. Now, so far we have learned that about J.J. Thomson and the electron, and Robert A. Millikan and the exact charge of an electron. Now, Ernest Rutherford's gold foil experiment found out that there was a nucleus and a positively charged proton in an atom. So now here is a diagram of the gold foil experiment. Now, as you can see, an alpha ray is being shot into gold foil and stopped by zinc sulfide. And now, the alpha ray hits the gold foil, and most of the times it goes through because most of the gold is made up of empty space. Now, some particles bounced back, like as you can see this one right here. It bounced back, and now the atom is made up of mostly empty space. But he found out that in the middle of the atom there was a positive charge, and Rutherford called this the positive bundle of matter, the nucleus. So, even though Ernest Rutherford, using the gold foil experiment, found out about the proton, he did not actually prove that there was a proton. Now, Goldstein and Wien discovered the proton using the cathode ray tube with the perforated cathode in the ray tube. Now, they discovered a collection of positively charged particles, and they finally discovered the proton. So now we have learned about the discovery of the proton and the electron. Now, the electron by J.J. Thomson and the proton by Goldstein and Wien. Now, Chadwick, he discovered the neutron, and he shot alpha particles at beryllium, and when they were shot at the beryllium, they made a beam form. Now, the beam was the exact same mass of a neutron, but it was made up of neutral particles, and this is how he discovered the neutron. So now we've learned about the proton, the neutron, and the electron in an atom. And now we're going to learn about Niels Bohr's energy levels. Niels Bohr has developed a new diagram of the atom, and he said that electrons can only be at a certain energy level, and they must gain a specific amount of energy to move to a higher level. This amount of energy is called a quantum. Now, this is his model, a picture of his model right here. Now, as you can see, the round thing is an atom, and in the middle there is a nucleus. And this first energy, n equals 1, is contained of 2 electrons. The second energy level is contained of 8 electrons. And this right here is moving down when a electron moves down in energy level, and this is moving up in energy level. And as you can see, it is the quantum and the photon. A photon is when it releases energy, when it is moving back up the energy levels. this is the periodic table of the elements. Now, on the periodic table, there is a period and a group. When you go down on the periodic table, you get periods. Now, this is period 1, 2, 3, 4, 5, 6, and 7. There are 7 periods on the periodic table. Now, across is group. And now there are there's groups A and there's the B group. Now, group A is the alkali metals, which is the first row, the alkali earth metals, which is the second row, and all the other rows on this side. It's just not including the middle rows in between, the transition metals. This is the transitions. These are the metalloids that are red, and these are the gases. And over here, which is cut off, are the noble gases. And these are transition metals. Now, group 1A, 2A, and it all goes all the way to 8A. And then there are also groups 3B, then it goes 4B, then it goes 5B, then it goes 6B, 7B, then there's 3 and 8B, then there's a 1B, then there's a 2B. Now, on the periodic table, under every element, you can see, here is a bigger picture of it. This is a boron. This is what every element looks like, but a little nicer. This is the symbol. It shows the symbol. Then it shows boron, which is the element name. Then it shows down here, it shows 10.811, which is the relative atomic mass. We will get to that later. And then up here is just the atomic number, sorry. And the atomic number is the amount of protons in this element. Lastly, we are going to talk about isotopes and ions. Now, isotopes are when an atom has more neutrons than it does protons. In a regular atom, there is the same number of protons and neutrons, but isotopes have either more or less neutrons in the atom. Now, ions is when there are either more or less electrons in an atom. A cation is when it is positively charged. So that means there are more protons than electrons. So pretty much you are losing electrons in the atom. And then anion is when it is negatively charged. And that is when there are more electrons in the atom than protons. Now, the last thing we are going to talk about today is relative atomic mass. As you saw on the periodic table, was for a boron was the relative atomic mass for it, 10.88 and not 811. And to calculate the relative atomic mass, we have this poster for you. And now this poster, it is isotopes average atomic mass. First, step 1, you want to percent to decimal, and that is, then step 2 is multiply by mass, and then step 3 is add it all up. So there, for example, we have oxygen. Oxygen has 30 different isotopes, and 99.75 of all the 759 of all isotopes is at 16 AMU, and it is oxygen. Just, well, we rounded the AMU, but it's more like 15.99, and then 909, then 0.037 at 16.99, then 0.204 at 17.99. And then, as we start with these values, we can calculate the average atomic mass by making 99.759% into 0.99759 times 16. That gets you 15.96. The next one gets you 0.00629. Then the last one gets you 0.0367. And when you add those all up, it gets you 16.00, which, if you're using significant figures, equals out into 16. And that is how you calculate relative atomic mass. We have had a fun experience today with atoms. I hope you enjoyed it more than we did.
Thanks for watching!